to have Dr. Dimos Kazanas with us today. For me, he's a long-time collaborator and a long-time friend. Dimos graduated from the University of Thessaloniki, and then he moved to the US, basically at Chicago University, where he finished his master's and PhD with Dave Schramm. And then he moved as a postdoctoral fellow to NASA and the University of Maryland, and he's there ever since because he became quickly a permanent member at the Goddard Space Flight Center. He has worked on too many things. I guess he is one of the Renaissance people of astrophysics, because he has worked on high-energy astrophysics, including everything, GRBs, AGNs, supernova remnants and neutrinos. Then he has worked earlier on cosmology, and maybe most people of the younger generation don't know that he was one of the founders of the inflation theory, along with Guth back in the 80s. He has worked also on modified gravity theories, and for all of these things, he has fresh ideas to put in the field, and I feel that he has a very unique way of looking at things. Many of the things that people think that are we take it for granted, for Dimos, they're not taken for granted. And this is, I think, his major contribution to the astrophysical thinking. He's also a Depisteron correspondent member of the University of the Academy of Athens since 2000. And with this, today he will talk about one of his latest things he's working on AGNs, warm absorbers, gamma rays, and he will try to combine many things of the AGN phenomenology. So please, Dimo, the stand is yours. Thank you.
Okay. All right. Thank you very much for the introduction. It's a pleasure to be able to see all these people around here, all the old friends. Let me see. I have to. Maybe in the future, one will be able to go out and walk into a room, put your Oculus goggles on, and see everybody, shake hands with everyone. For the time being, we'll just be limited to Zoom, and we'll see now. I have to find where my screen is so that I can. Let me see, AGN. No, that's not the one. Let me close this. I found it. I assume, has it appeared yet?
Yes, but it's not full screen. So.
Well, now it is full screen?
Yes.
Okay, so let's say, well, many of the people in the audience have worked on AGN, so it's another take on AGN. And well, I'll try to convince you that there is something to be said about the X-ray spectroscopy, and it gives us an indication of the underlying structure, which may be applicable to many AGN subfields. So collaborators here, most of the calculations you will show about ionization structure of AGN will be done by former postdoc and now Professor James Madison Keigo Fukumura, in collaboration with Chris Schrader, who provided lots of input knowledge, basically. Ehud Behar is the X-ray spectroscopist. He's with whom we started this particular enterprise. He is at Technion. Yannis Kondopoulos, well, we use his models from his thesis, so he's a co-author in a number of the papers. And That's the person we go to when we ask questions about MHD winds. And more recently with Apostolos and Stella, we try to apply the same structures in blazars. So, oh, I'm sorry, I forgot also. These are also have buried to, well, to dust formation in AGN. You've heard of the AGN dusty tori, and Arkas Arangi was Eliduek's postdoc, who is familiar with dust production. So we've applied the same models to producing dust in AGN. So, so the question is, what constitutes AGN phenomenology? And then I go that. Well, phenomenology of AGN has myriads of facts. So one has to be a little bit careful now. What are shapes? That you've probably seen this this particular picture, which is a cartoon of an AGN in the same way that the Donald Duck is a cartoon of a duck. And it's another a little more refined version of this particular picture. And we also have galactic black holes, which basically have the same structure of an accretion, black hole with an accretion disk and perhaps a jet, with sizes which are much too small. So therefore, in order to understand the physics, we resort to either spectroscopy, like we do in spectroscopic binaries, and or time variation. So we can try to basically invert the problem to understand the structure of the, oh, here's the galactic black holes. Second thing is, besides the shapes, we have now the SEDs. SEDs, the spectral energy distribution, and here is the average SED of an AGN. It covers, let's see, from 10 to the 11 to 10 to the 18, and maybe a little wider. That's for radio quiet ones. About a dozen decades in energy, and you're familiar with that as a there is something called the blue bump. Presumably that's the accretion disk that presumably and usually is the most luminous part of the AGN. Apparently that comes, it's modeled as that piece that is being closest to the ISCO, the innermost stable orbit. However, there's also X-rays and there's also infrared. And of course, there is radio emission and radio quiet. I don't want to talk too much about this issue, but in radio quiet, the radio emission is about 10 to the minus 6 of the bolometric, as you can see from up here. In radio loud, actually, there's a continuity of the spectrum from 10 to 12 all the way to 10 to 9. So it's about 1,000 times less luminosity, not photons, luminosity in radio than it is in the optical UV, roughly. However, that's not the case. I mean, there's a rather wide variety of SEDs. So here's now a low luminosity Seyfert. And you can see here that the X-rays are more luminous than the blue bump. Well, how is that possible? Well, the models that don't tell you anything about that. And hopefully I'll have something to, well, I'll try to convince you that we have some kind of inroads into this particular issue. We don't have all the answers yet, but we have some kind of idea as to why now there is another AGN, a quasar, where the blue bump, so-called, that's the observations. If you try to fit a model, you go over here, it's about 30 times more luminous than the X-rays. Usually what people are saying is, oh, we have a corona, and the ratio of luminosity's corona to disk is arbitrary. And we use that to simply, so here's the answer to the picture. So we have now a corona, which is the innermost part of the AGN. It's above the disk, apparently. Here's the blue bump, is the innermost part of the disk. And of course, we have infrared emission because part of the disk is reprocessed in this strange structure. Is called the torus. And why is the torus strange? Is because the temperature of the torus is of the order of a few hundreds degrees or tens of degrees However, from geometry, just from the statistics, we know that it has to have a height which is comparable to size, which means, because it's about a parsec away, that the random velocities of the material, if that was in hydrostatic equilibrium, should be approximately 300 kilometers a second. And it should have column which is opacity of close to 1, which means if that was random and the opacity is the column of all these clouds, whatever it is close to 1, that means, and they have random motions to have a high z, they should collide within one orbit. And therefore, the temperature of that should be the kinetic temperature of 300 kilometers per second. That's 10 keV or more than that. That's not what we see. We see cold material. So that bears to what I'm going to say shortly afterwards. Now we have the near part of the AGN has the optical UV and has the X-rays. We know that the infrared emission, the torus, comes from far away. So if we want to understand and it's generally considered being reprocessing of the radiation that comes from nearby, and therefore we don't have to worry about the where the radiation is produced. Clearly, this part is reprocessing, but we don't understand actually how the optical and the X-rays, if they're related at all. In general, and at the end, you can correct me if there's a theory. I think in general, one assumes that there is some part of the viscous energy that goes to the disk through magnetic fields is released in the corona, and therefore that's the AGN. That's the corona and the UV, and that is sort of arbitrary. The ratio is arbitrary. The ratio is because it's so important. We have one parameter to characterize that. That's called the alpha of x. Is the ratio of fluxes between 2500 angstroms to 2 keV. Basically, is the logarithmic. So if you like, is the logarithmic slope between optical UV and X-rays. So what are the other parts of the phenomenology? I already discussed that as the tori. That's now it's just something new we have, the M sigma relation. I don't think I'm going to have much time to talk about that, but what I suspect it has bearing to this relation too. It's one thing I would like to discuss here. So people have measured the black hole mass, and they found it correlates very well with the dispersion velocity of the surrounding, not galaxy, surrounding spheroid. Now, they also done the same thing for AGN, and they found out that the AGN they had masses which were below that. However, that was done by reverberation mapping. Reverberation mapping, you find basically how long does it take for a line to respond to variation. The continuum, you assume the lines are in Keplerian orbits, and therefore you calculate the mass from the time lag and the observed velocities. If that's the case, then F should be about 1. Well, it turned out that with F equals 1, all those guys were coming down here. So immediately they say, oh, we must have been issues which we don't understand. So they put F equals 5.2 to shift everything in agreement. And that's an issue I bring up because I totally disagree with this approach. Another issue, of course, of the AGN is the AGN lines. That's a totally different subject. I don't think it's been discussed recently. It's been discussed way back in the 80s and the 90s a lot. But now, other than that's the optical lines, people discuss more about the X-ray lines, essentially the iron K, because that is related to the spin of the underlying black hole. I won't say very much about the lines. I don't think I'll have time. I could say a few things, but I don't think there will be time to discuss lines at this point. Let me give you a very brief review of accretion disks, because they are at the center of what produces the luminosity of the AGN. So we know that material has to flow in and therefore has to lose its angular momentum, and that has to do with the torque that you have, and the torque has to do with the stress energy momentum tensor, which we have a prescription for. It is proportional to the pressure. That's the standard Sakura-Sunyaev, and this is the the torque. That tells you basically angular momentum transfer. We also have hydrostatic equilibrium. It tells you basically how high is the disk, the height to radius ratio of the disk. And if you have the stress energy momentum tensor, you multiply that with a shear, and you can calculate, that's in the standard books, you can calculate how much energy produced from both sides of the disk. That's the part 2 here, from each side of the disk. And there's a standard expression, 3/4 pi, and if you do per side, it will be 3/8 pi. Now you can multiply by the area of that part, and you find out that basically the how much is the energy released per unit in a ring, or from 0 to that area, and goes, do the integral here, goes like 3/2 m dot gm over r1. R1 is the radius of which you're looking at. You have to realize that this is not exactly what you expect from a material released, potential energy released from infinity to that point. That is approximately that. It's gmm dot over r1. However, it's not only that. The energy available for heat, due to the virial theorem, which tells you it's only half of that. It's only 1/2 of this expression here. The other half, it remains as kinetic energy to sink further in. So the question now here is, what's the discrepancy of this factor of 3/2? And that is a point I'd like to, that's why I went through all this analysis here. There's extra energy due to the viscous stresses transfer not only energy, not only angular momentum, they also transfer energy. And the energy they transfer is the torque times omega, and the torque is this quantity we discussed that earlier, multiplied by the area, and that is gmm dot over r. And if you add it to the 1/2 gmm dot over r from the energy released from the gravitational potential, then you get a 3/2. And this is, that's not explicitly discussed in books, but this expression is discussed in books, and in generally assume that all that energy is dissipated locally. But if you read Blanford and Bigelman, you find out that they suggest that maybe some of that energy actually is, escapes to infinity and carries with it energy and angular momentum, and that's the kind of the picture I'd like to have in my head. The other thing, before we go into more details, is that accretion flows, or winds in that sense, they can be, just a second, please. They can be written in non-dimensional units if you express if you scale all the radii with the Schwarzschild radius. So therefore, instead of writing r, you write r over Schwarzschild radius. Immediately, the velocity depends only on x to the -1/2. Express all the radiation in terms of the Eddington radiation, which contains the Schwarzschild radius, therefore the mass, and all the accretion rates or the mass flow rates normalized to the Eddington accretion rate. So now we have a density profile, which let's assume goes like a power law. At x = 1, we have exactly this scaling. That is, if material is free falling or on the horizon, the column density of the material will be simply proportional to Schwarzschild radius times the cross section of the Thomson cross section. I'm sorry, I went back. You can scale again the mass flux in the wind, density times area squared times the mass of the proton velocity, and now you can calculate the column, or the optical depth if you like, and you realize that's independent of the mass. So that is, whatever has to do with radiative transfer, that is not dependent on the mass, and therefore, for this reason, we can deal with small black holes and large black holes as far as radiation transfer is emitted, or absolute luminosity is emitted, relative to Eddington luminosity emitted, irrespective of the mass. Now, because I'm going to talk about line emission, I have to say something about something that's called the ionization parameter. It's the ratio of photons to electrons. The photon flux, L over R squared, tells you how fast you kick out, electrons out of a given orbit of the atom, and the density tells you how fast they recombine. You try to put all undimensional units, the mass cancels out, and the m dot cancels out if your luminosity is proportional to the m dot. If your luminosity is proportional to m dot square, like we have in ADAF, then there is an m dot here. But in general, this ratio is independent of m and m dot. And that's important if you want to calculate, understanding the ionization structure of winds. That's the other part of the phenomenology, is winds. About 50% of AGN, that was known before from the UV absorbers. They have winds. Some of them, it's called BAL QSOs, they have velocities up to 10,000 kilometers a second. However, most of them, usually here is the IU spectrum of NGC 4151. It's only a few thousand kilometers per second. You can see a big absorption here in the overall profile. There's some more absorbers a little farther down. However, if you go to X-ray lines, then you find out this is actually a BAL quasar, which is it's been lensed. It's a gravitational lensing, and therefore you can, even though it's a higher redshift quasar, you can see that. That was done by George Chartas, these observations, and collaborators. And I'm sorry. The interesting thing is, and I will get back to that, that the velocity of these absorbers, which presumably are RN25, they've been identified as such, increases when the spectrum becomes steeper. That is part of the phenomenology. That was done earlier in the Chandra, shortly after its launch. We've seen this kind of X-ray absorbers with ASCA. Of course, the resolution of ASCA was not very terribly good, and the throughput was not very large. However, they've seen lots of them with various ionization states, and therefore, and because the temperature of the gas that will produce these transitions, it was of the order of a few hundreds of thousands of degrees, they call them warm absorbers. So since the mid-90s, these kind of transitions, they've been given the name warm absorbers. With the launch of Chandra now, we have much higher throughput, and of course AGN and XMM Newton. This is now Chandra HETG, high energy transmission grading. You can see now it's a mess. I mean, look how many lines there are. You can see the entire sequence of all these lines, and they are blue shifted. So these guys are not sitting there. Here's the zero velocity. That's for magnesium 13. Let me see. I have to put my glasses. No, magnesium 11. Here's a silicon 13. Here's the zero velocity, but most of the absorption happens at around 2,000 kilometers a second. Here, most of the velocity happens at lower velocities, but there is still absorption at around 2,000. And the question is, what can we do with this mess? Usually, I don't show here the area which is near 1 or 2 angstroms. That's basically, spectroscopists use angstroms instead of energy. That's the iron K. And there is absorption in iron K, but all these other ions are at lower ionization state. That is, the cross-section for ionization is larger, and therefore you can ionize them with smaller flux, so therefore they must be farther away. Iron K has smaller cross-section for ionization, so this is a higher ionization transition, is much closer to the black hole. So usually people will do, they say, oh, we must have some gas at high ionization, some gas at low ionization, and they try to sort of make a guess of what the structure of the gas of this material is in AGN. So this is on the left is an AGN spectrum. The same thing we see also in galactic black holes. That's source is GRO 1655-40. We don't see them as often, but on occasion in their soft state, we see these lines. And you can see here's the iron 26, iron 25, some even higher ionization transitions. And you can go all the way to lower ionization transitions like neon 10. The data is the black line, the blue line is a fit. I'll talk about it for sure in a few transparencies down the road. Again, high ionization, low ionization, what do we do about that? And before I discuss what to do about that, I have to say a few words for the importance of X-ray spectroscopy, which may be obvious to many of you, maybe most of you, but it took me many years before I realized that. The presence of a given ion, as I mentioned earlier, depends on this parameter, ionization parameter, L over nr squared. N is the density of the gas, R is the distance from the black hole. Of course, you can take 1 power of R with N, you make it a column density. The advantage of X-ray spectroscopy is that it can access all states of ionization, from neutral iron to highly ionized iron. Those are about 5 or 6 decays in Xi, within a factor of 20 in X-ray energy. So if you have basically a detector that covers from iron K to half a keV, you can essentially see the ionization structure of material will be imprinted in the ionization structure of material that covers about 6 decades in ionization parameter, and depending on how the density varies along your line of sight, 5 or 6 decades in R along your line of sight. This is something that really is very important in understanding the distribution, the structure of AGN. And of course, all these, as I showed you earlier, they're blue shifted with different velocities. So this is what Bihar was trying to do. He did actually, and the way he did it, instead of taking some region here with some high ionization, low ionization, he assumed there is a column which is a power law in the log of Xi. It's called absorption measure distribution. So let's assume there's a continuum of densities, and therefore there will be a continuum of ionization parameters. And what we really measure is how deep the lines are, and therefore measure the column of that. And so he and his collaborators, they basically tried to parameterize all the lines, do a global fit of all the lines with one parameter, this parameter P, which is the slope of the absorption measure distribution, and that's the distribution. So you take, say, iron 26, you find all the ions of iron, those are the black lines. You find how much column you see from the iron absorption. You divide by the abundance of iron, and you find out what's the column of the hydrogen that you have locally as a function of Xi or as a function of KT, if you like. And you can do that for all sorts of elements, and you find this kind of distribution. It says that the column doesn't seem to change with Xi, which means that implies something about the density of the material that's along your line of sight. If your column doesn't change, the density goes like 1 over R roughly. So you have equal density per decade. And he did that with these 5 AGNs, and you found out that this parameter P varies between almost 0 that we have for this object and 0.29. And if you convert that into density, the density varies between R to the -1 and R to the -1.25. This is very strange. So basically, that's when Bihar and I we met, because he was at Goddard at the time, and I told him, well, we're trying to basically go out and take calculate, because I knew about photoionization, warm absorbers, and so on and so forth. And every time you find something that has, like the quasar lines, if you like, and you have something has to do with ionization, you find something which is a little bit strange, then that doesn't does not fit well a single region with a single column density, then you want to think of density gradients. So I was thinking of taking the Yanis's thesis, which has winds basically, and try to calculate the ionization. And because his thesis has essentially density profiles, which are the -1, I said, this is exactly what the stuff that we're doing. So that's how we start our collaboration with Bihar. So let's go and do a little bit of a analysis here. We have Xi goes n over r square. We express that in terms of column density. So for the column density, which is L over r Xi, this is constant, which means r times Xi is constant. And therefore, from that, you get that the density goes like 1 over r, not 1 over r squared. And that's strange because you have a wind. So winds, they tend to have, once you go past the accelerating regions, they should go 1 over r squared. Of course, that means that the column density then drops like 1 over r. And therefore, if you try to go far away, then you should have very little column. And we see we have column everywhere. Then you can also calculate the m dot. And I showed you earlier the dimensionless m dot. In this particular case, if n goes like 1 over r, and this is a wind now because have absorption, blue shift absorptions, then you find out the m dot goes like r to the 1/2. The m dot in the wind increases outward. So, and this is true actually with Yanis's thesis, and it's also true with a paper by Blafford and Bigelman. That doesn't mean that the wind is increasing outwards. We have material try to come in from the outside, but because the viscous stresses transfer also energy, only a small fraction, well, half make it into toward the black hole at every part in every decade in radius, if you like. The other half, because there's a received of that energy, escapes in the wind and carries with it the requisite angular momentum, so the rest of the material can come in. Now, Yanis' thesis, of course, assumes the disk is a Keplerian disk, puts the magnetic field through, lets the magnetic field rotate, and he calculates the wind profile. The reality is more complicated, of course. So these winds were started by Blanford and Payne. Janison with his advisor, they did this more improved, enlarged winds, which allow different profiles. And Koenig and Cartier, at the same time, independent of Yanis, I think, they concocted similar winds, and they said that this far away beyond the dust sublimation region, these winds will have dust, and therefore they will be the their models of the AGN tori. And I think to me that's the only thing that really makes any sense, because those, in order to have basically material high Z and low temperature, this must be moving upward. And it's moving upward because of the magnetic fields, basically. That's so it is part of the wind that we have. If the wind now, if the density goes, if the wind has a m dot which goes like r to the 1/2, then which means that the disk must have a m dot which goes in a similar way, because at every point in the flow, the wind shares its m dot with a disk. Exactly the amount, it doesn't matter for the scaling, we assumed half. Then the most of the m dot comes from larger radii, but the energy still comes from the small radii. So if you have outflows from small radii, they don't go like 1 over r. Now they go like r to the -1/2. In scaling, you use the scaling. If you go close to the Schwarzschild radius, then that's basically have the same scale as before, and they have roughly equal momentum per decade. So the flows are not driven radiatively. Radiatively, winds some of you know that they have a velocity which goes something like that. The R star is the launching radius of the wind, and therefore one starts with some small velocity and then asymptotically achieves the asymptotic velocity of the wind. And that's at that point, the density drops like 1/r. Earlier on, the density drops much slower, and therefore, which means that the ionization parameter would have been smaller there. So we can calculate now the AMD for these winds, and you find out that that basically AMD decreases with increasing ionization. That's not what we find. So therefore, what we found earlier is that the AMD is constant, or if anything else, it's toward the black hole where the ionization parameter is higher, the column is higher. The winds, radiatively driven winds or thermally driven winds, show exactly the opposite behavior. So this is indication that we should not in all cases, of course. If you're close to the Eddington luminosity, then you may have something which is different. But if you're far from Eddington luminosity, I cannot consider the winds are driven radiatively. Well, of course, that depends on the observations. You do the observations, you calculate the AMD if you have X-ray spectroscopy, and it's accurate enough. And then that will tell you roughly what is the distribution of density along the line of sight. So this is now how the shape of MHD winds look like. They have a very high gradient in the theta direction. Along every line, the density goes like the same power law. As you increase the inclination, the power law density remains, but the normalization increases. And this is exactly what we do. This is basically calculation from one of our papers. So we take a line of sight from Yanis's thesis, if you like. We solve it again. We calculate the honest-to-God wind with some arbitrary functions about the mass flux and so on and so forth, so that we have the correct lines. This is the magnetic field lines now for the solution. This is the disk, but this is now in linear dimension. This is in logarithmic, just to show how they look like schematically. This is part of the log C. The velocities, as you can see, drop like square root of R, and this is the torus. It's sufficiently far away that we have dust production, and therefore this as a toroidal structure. Now, so we take basically a line of sight, we split it logarithmically in radius, we calculate some fraction of 1.15 per box that we have. We call this photoionization parameter called X star that Tim Kalman developed. We calculate the ionization structure of the winds, and then we know the opacities. We use that. This is almost plane parallel geometry, and we pass the radiation, do very simple radiative transfer. We pass to the next column, the next slab. Same thing there. Now the radiation that comes in, of course, has some energies are diminished because of the absorption that they suffered along the way, and so on and so forth. We go outwards until we calculate the ionization structure of the entire wind along our line of sight. Here's the two-dimensional ionization structure. We don't have to worry too much about it. And here is now the model that we have for GRO 1655-40. That's the best absorption spectrum we have so far in terms of signal to noise. And we now we leave a parameter S, the density profile, arbitrary. We try the relation between the index of the absorption measure distribution and the density distribution is essentially this. So if your P is equal to 0, I mean, you have this flat AMD I showed you earlier, then basically S is equal to -1. And the density profile goes like out to minus S. We leave S free. we assume the velocities go like r to the minus a half, and we try to fit these lines that you see. That's the blue line is the fit for all the ions at the same time. The particular object has also a well-known inclination, so we know at what angle and which part of the which line we are. We are at about 70-degree angle here, and therefore we have, for a given particular model, we have everything we know. The only uncertainty is N0, which gives you the overall mass flux in the wind, and S. And by fitting all that, we found that S is the best S we get is about 1.15. But you have to remember that all the structure of these lines, both in velocity and in depth, are solved by the same three parameters: the 70 degrees, okay, and N0 and S. That's it. We don't go to fit individual lines. Now out here, for example, well, we predict there should be more line, and there isn't as much. And here the velocity is a little bit off. We're not doing as good a job at this higher ionization features. For a single power law, I think that's very good fit. It may not be true for all AGN or for all winds that we measure, but for this particular case, we lucked out, but it gives us confidence that we use basically here the scaled down versions that we use to fit in AGN. So in this diagram, I show you how the line shape develops as you're very close to the black hole. Of course, let me go one. Oh, okay. You're very close to the black hole, then high ionization. There is some column, but it's very small. Velocity is very large, but the column is small. And as you go farther out, then you build up more iron 26 iron. The column becomes deeper, and that's basically what you expect to see. That's the fit. The red line is the fit at infinity, and the crosses are the data. The same we've done also for the neon line. So the neon 10 line is this one. And you can see now these numbers here tell you the distance from the black hole. And you can see that in centimeters, that's the log of the distance in centimeters. This is a binary system, so the separation is about 10 to 12 or so you can see now that the neon line comes from farther out than the iron line. Now we also have the profiles. These two lines show you the rest frame wavelength, and from the peak here of the absorption and from its blue shift, we can calculate this velocity to be about 1,700 kilometers per second. And for the neon is about 250. We've done the same thing for objects that have high signal to noise. That's the NGC 3783. I show you some lines here. Some lines that fit well. Sometimes this particular doesn't fit very well. I don't know if it's an issue of this aluminum here. I don't know if it's an issue of abundances. We assume solar abundances for all those similar values. So here is exactly the ionization structure that I was telling you about. You can see now you're very close to the black hole. You have very little iron 26, and the line profile is a convolution of this ionization structure with a wind velocity, which drops like r to the minus a half. So we've done that for all these ions and so on and so forth. That's how I did the fit. And this is the numerical fit to the observed velocities. This is the fit that we get from the scaling. If the density drops like r to the minus a half, then from the scaling, you can calculate what the velocity should be. And the velocity is steeper than what we observe. So one has to be a little bit more careful before one makes pronouncements about the scaling of now we have, besides the density profile, we now also have velocity information. So you have to combine the two, and that's what comes out here. This is also optical lines. I don't want to discuss optical UV lines to discuss that. So we've done the same thing now for we've done for a galactic source, and we've done for a Seyfert. Let's do it. We've done it also for a BAL quasar. What's the difference of BAL quasar? It has the much higher in absolute value alpha x. That is, for a given mass flux, which is give you the the UV luminosity, it has less X-rays. And why is that so? Well, we don't know. I will discuss that. But once you do that, then you realize that basically the wind, if I wanna go back here, if you have less X-rays, then this line will be shifted to smaller velocities, higher, smaller distances, higher velocities. So this is our take on what makes a BL quasar. For some reason that we don't know, this is much less ionizing luminosity, and therefore all the velocity structure now moves closer and therefore higher velocity. And we've done that. So this is the wind structure, but in log-log space. So all these ionization lines are like this, and the line of sight goes along this direction and cuts first through the iron, which is closer to the smaller radii, and then through carbon-4, which is farther out. Let me see. And this is now the diagram I showed you earlier. Oops, I'm sorry. This is the Chandra measurements of APM82, the one that George Chartas showed, who found that when the photon index becomes higher, meaning the spectrum becomes softer, then the velocity becomes higher. And these are his data. This is our model. And the reason it becomes higher because, again, there's not enough ionizing flux. And therefore, the first distance that you find iron 26 is very close, or 25 is very closer to the black hole with the steeper spectrum and therefore higher velocity. The same happens with the carbon-4. And if, on the other hand, now it's a model here, if we fix the gamma to 2 the alpha x to 2, and we change the, I'm sorry, we fix the spectrum to 2, and we change the alpha x, we put more X-rays, then the velocities, which is down here, you see it becomes smaller and smaller and smaller and smaller. The same is also with carbon-4. And by the time we reach here 1.6, this is a Seyfert, we have velocity similar to what we see observed in Seyferts. So this is the, I'll skip this. So this is now the bottom line here, that the absorber velocity. So we have now, from X-ray spectroscopy, we have absorption features, a different ionization parameter, high ionization, iron 25, 26, lower ionization, neon 10, oxygen 7, oxygen 8. The velocities have different, the velocity of each ion is different, and higher velocity tells you you're closer in, and therefore more X-rays means that you expect the absorbers to be at lower velocities, and that's what we see here, of course. And this is an X-ray source. Most of the luminosity here is in the X-rays. So we don't have the alpha x anymore. All the luminosity is here. So what we say here is, and some people are kind of, they don't feel comfortable about that. We say that there is wind all the way from V equals C over 2, whatever it is, all the way to 1,000 kilometers a second. That corresponds to the iron. It's just we don't see any of that because it's highly ionized. So we have essentially what we suggested is here. We have again an MHD wind that starts from very close to the black hole, maybe in the hard state also gives you some radio jets. But we don't see this wind until you go sufficiently far away so that the ionization parameter, which drops drops fast with density, which drops slower than the velocity, gives you enough ionization to produce iron 25, 26, and of course all the ions further down. So, so here we have now that density profiles which are not consistent with material being blown out from regions of rather limited extent. All these observations indicate that we have winds that come across from the entire wind domain, which may be covered 5 or 6 decades. So what are the implications of the global structure? I mentioned earlier that this simple scaling for the wind shows that the wind increases outward, which means that the accretion rate, if that every decade they share the amount of matter that they allow in and out, must decrease with R. So therefore, as the m dot decreases, there will be some region interior to which the m dot is smaller than what you need to have an ADAF. For all those you see, the ADAF was basically introduced by Narayan, and these accretion flows for which basically the energy transfer from ions to electrons is slower than the inflow velocity, the viscous time scale, if you like, the viscous. And therefore, a good fraction of the energy stored in thermal motions does not have time to become radiation, and therefore is advected into the black hole. And once you do the order of magnitude estimates, you find out that both scales scale basically with m the same way, and therefore the ratio of the cooling time to the inflow time for something which is thick, it's independent of the mass and depends only on m dot, as we've been arguing all along the past half hour or so. And therefore, if your m dot is smaller than alpha squared, then you never cool. The disk remains hot all along. On the other hand, if your m dot is constant, then it doesn't matter. I mean, if either you have all hot flow or all cold flow. Once you start cold, there's no way to become hot because the ADAF condition is a condition on the accretion rate. But here now we have, in a simple-minded way, we saw that we have m dot that depends on the distance from the black hole. So as m dot decreases because a good fraction of the available mass escapes in the wind, carrying away angular momentum and energy, then this material now, because this magnetic field was annihilated, they can hit the material, even though it's not very hot far away, it can become hot. It can convert to an ADAF. And therefore, now, if that's the case, the X-rays are not independent component of the accretion rate. I mean, my understanding, even now, is that the corona is something which is independent of the rest of the accretion disk. I see the blue bump, and then I see how much X-rays there are, and I arrange that the X-rays have enough material, have enough energy somehow to power the X-rays, and the blue bump has enough viscous energy to power the blue bump. This is not the case here. The flow separates into a viscous component at large radii and an ADAF component at small radii at some transition radius R of t. All that is written in a paper that was edited by Yanis, Denis Gabuzla, and Nick Kilafis. So the transition radius, as I said, the local accretion rate has to become smaller than alpha squared. So m dot is the accretion rate at the inner edge. We discussed that m dot depends on distance. M dot 0 is the accretion rate at the near the black hole. You can normalize it to the accretion rate at the outer edge. It doesn't make any difference. That decreases with R, with X. At some point, this becomes smaller than alpha squared. Then you have an ADAF. And that is the issue that I would like to discuss. So now there is a viscous luminosity, which is m dot You multiply by the mass, of course, because the mass gives you the total scale of the luminosity, but the mass cancels out here. It's m dot over x, integrated over the log of x. That's the viscous disk luminosity all the way from the transition radius outward. And of course, we have also the ADAF luminosity, which is from the transition rate inward to the ISCO. And now we have an additional factor of m dot because the efficiency of an ADAF is proportional to m dot. And we can calculate the ratio. This ratio R is the luminosity in the viscous disk to the luminosity in the ADAF. And with this, we can calculate that. And here's a plot I have. For small m dot, small outward, which means a small inward, assuming steady state, there'll be a transition radius that will be at around 50 or 100 Rg. This now, that's the ratio. We have roughly equal energy, equal luminosity between the blue bump and the X-rays. I claim, I venture to claim that this is a model for 5548. That's a relatively low luminosity cipher. The same is true also for 4151. However, as we increase the outer m dot and we increase the m dot everywhere, then the transition radius comes closer and closer and closer, and then the dominance of the blue bump increases. And this is another AGN, I forget now the number, in which you can see that the luminosity in the blue bump is at least 10 times or maybe more than the X-rays. And of course, that has been discussed in the literature. Those people who are familiar with this particular paper, that has been discussed by ASIN, which is Narayan student, Narayan and McClintock. And they say that we can explain the phenomenology if we assume that the disk truncates and converts into an ADAF interior to a given radius, which decreases as the luminosity increases. Well, I explained to you why this would be the case, and the case for that is because of winds. And out here, I show the spectra. So here's the low hard state, and here's the variability spectrum. There's a lot of MHD stuff going on, and most of the variability peaks at the viscous time or the dynamical time of this material here. And you can see it also has a QPO, and then it dies out. As you increase the m dot, and this is the kind of a, I'm sorry, backwards. Come on. This is a figure that I've drawn by hand. The accretion, the ADAF component has H over R comparable to the radius that you are, and therefore in low luminosity, the truncation is at large radii. You're in the blue part, and as you increase the m dot, you become the high state. Closer in, the spectrum now becomes a 1 over f spectrum. This is the power times frequency. And eventually you come close to the Eddington luminosity. Then the disk is very close to the black hole, and it's also thick because you're close to Eddington luminosity. The spectrum, of course, again, is dominated by this thermal component. There's very little material coming in because basically all the X-rays must come now from this region here, very close to the between the non-thermal has to come between the black hole and the inner edge of the accretion disk. So this general idea is consistent with the with what we observe. So now we have two upcoming missions. One is CRISM X-ray. I forget now the acronym. It's basically a calorimeter, high resolution calorimeter, resolution probably 2 eV. That'll be flown in the next couple of years by the Japanese. Goddard contributes the calorimeter here. As a sad story, this has been attempted 3 times, and I'm sorry, 2 times, and it has failed. So what we've done here, we've taken this spectrum. That's Kagu's calculation. That's the spectrum of GRO 1655 with Chandra. That's the one we fit. And we pass it, the red line is the exact calculation. We pass it through the response function of CRISM for, this is 10 kiloseconds, and for 45 for 45 kiloseconds here, and for, for 10 kiloseconds, you see higher noise, and with 45 kiloseconds, lower noise. You can see all this structure out here that there is substructure here in these lines, because one is a triplet and the other one is doublet or whatever it is. I forget the precise nomenclature in X-rays, but you can see this structure with a higher resolution instrument, and we can zoom in, and now you can see that even better. And that's with a 45 kilosecond CRISM and a 10 kilosecond Athena observation. Athena will fly in the early 30s, I assume. And now you can see basically the substructure that we see we have in those particular transitions. Now, this will cover the entire X-ray spectrum, and there will be plenty of information to try to fit. As I said, so far we use a single power law. I don't expect it will be a single power law, but then you start adding parameters, then you lose transparency. Not transparency. You lose the broad view of the structure. But I'm sure there'll be plenty of work here for spectroscopists, and we're looking forward to see what these missions are going to produce. So now I'll say, as I'm running late, let's say a few things about blazars. The blazars are basically, they have the same structure. That's our presumption. We presume that the blazars have the same wind structure, except for the fact that there's some accretion field lines, some field lines that go through a rotating black hole. And Yanis with Antonis Nathanael, they have solved for the magnetospheres of these structures. You can go and look at their papers. And these structures now produce relativistic jets. In trying to fit work about these issues, we say that it's a blob. That's part of a jet, of course, that moves relativistically, and it has some kind of thermal distribution, which we don't really know what it is exactly, but we try to solve for that. But you have now the continuum radiation is reprocessed here, and of course it's isotropized. However, if you move relativistically along this direction, then all those photons you see coming up from the forward direction, and they come up with a nomenclature of external Compton contribution. So out here you have synchrotron emission from the blob, and you have synchrotron self-Compton, and you have external Compton. And in the luminous blazars, this external Compton seems to dominate. If you look from the side, you see again absorption, X-ray absorption lines, and those guys are called broadline radio galaxies, and they do have X-ray absorbers. If you look from near the axis of the jet, you don't see those lines for one reason, because the column density of the wind is very, very small, close to the axis. So therefore, there's not enough column, and of course, there's much higher ionization there. And the blazars now, there was discovered in earnest with the launch of GRO, Compton Gamma Ray Observatory. Even with the 66 observations, they found there is a correlation between so they have very broad distribution functions in the photons. They have two humps. One, they start all the way from radio observations to TeV gamma rays, if you like. Not all of them, but certainly all of them GeV, which is around here. And they have two components, two humps. One is considered to be the synchrotron emission, and the other one is supposed to be Compton emission. And people found that the more luminous blazars have more gamma ray luminosity. So the luminosity of the blazar correlates with the frequency of the synchrotron peak emission, and they call it the Blazar sequence. Now with the Fermi lot, we have close to 3,000 blazars. And this is the statistics that we have. In order to fit each of these spectrum, you need approximately 7 parameters. After you do the statistics of 3,000 blazars, you have essentially this correlation. This is a 1-parameter family. Of course, there has a width here. It's a 1-parameter family, which means that somehow there's probably a similarity issue underlying, or there are internal relations that basically cancel out the correlations among the parameters. This is a 1-parameter family, and that's what Stella and Apostolos and I would try to understand. This is now the same thing, the gamma ray luminosity here as a function of the gamma ray slope. This particular, so what we have now here, we have a correlation between 2 spectral aspects of it. One frequency, which is the frequency of the peak emission, and the slope of the gamma rays. No mass, nothing, just only spectral parameters, and it's 1-parameter family. So if we want to understand blazars, we have to understand it in this context. And here is some, of course, you can go through all this relation I discussed, and you find out that all the spectra are sort of mass independent to some extent. They depend mainly on m dot, and the 3 spectra that Stella calculated here have m dot 0.3, 0.03, and 0.003. And you can see that these are the 3 crosses that I have here. So to 0th order, we kind of reproduce the general behavior. This is the, this piece shows you the external component of this component. So this is mainly SSC. The external photons, because my m dot in the wind is so small, there's very little feedback from the wind onto the blob, and therefore the external component is small. As you increase the m dot from 0.003 to 0.03, then you have more contribution to the external component. And then you go to 0.3, then essentially all the gamma ray contribution is equal to the external component luminosity. And you can see now the spectrum, this is the Fermi lat band. You can see it changes from something which increases here with mu of nu to something which is almost flat to something which is steep, and that covers this medium. I don't think I have time to talk about anything else, so let me just kind of go through the summary and conclusions. Mounting evidence that's a ubiquitous presence of outflows with accreting black holes. The broad range of ionizing species and velocities implying a broad range of launching radii. This is by and large, there may be situations where the winds are driven by radiation pressure, especially if you're close to Eddington, but by and large are not radiatively driven winds. As I discussed, these scalings imply that the mass flux in the wind increases outward. And you may have heard that in many cases where they've done spectroscopy, they found out that the mass flux in the wind is much higher than what you need to power the black hole. This is essentially what I just discussed, that the m dot increases outward or decreases inward, if you like. So therefore, by the time you go to the black hole, you have very little left. So this implies that we discussed that. That's these flows are not called ADAF, they're called adios. Direction, inflow, outflow solutions. That's, I guess, something that Mitch Bigelman came up, or well, maybe Blanford came up with, I don't know. But in their paper, they call them adios. And I think that is the essence of this, of the entire phenomenology, which of course implies that there's everything we know about AGN is basically magnetically driven. There's a transition radius that determines now where your truncation radius of the viscous disk starts and the ADAF component or adios component starts. And now, because of that, the X-ray emission is part of the overall accretion dynamic. It's not something you put independently with a light bulb up there to explain your X-ray observations. It has to be consistently tied to the accretion rate of which is the blue bump. And I'm sort of distressed in people who provide X-rays, X-ray analysis of AGN with XMM Newton. And they have the data, the OM data, they give you the optical UV, and they totally ignore it. So they give you all the X-rays, and you analyze them to death. And a good fraction of the information, the global information, which is contained in the UV, is completely thrown out of the window. So, so I said, get all my frustrations out here. So the wind ionization properties depend now on the spectrum. So if you have, m dot is large and you squeeze your X-rays very close to the horizon, you have very little X-rays, and therefore now you're going to have high velocities in the absorbers. You have BAELs. So otherwise, you have a moderate X-ray content, and you have something that you call them UFOs, worm absorbers, and so on and so forth. The galactic black holes must have very low velocities because they're luminosity dominated by the X-rays. So these models are scale independent as long as now, and they can cover the range between 10 and 10 to the 9 solar masses with one particular parameter m dot over m dot Eddington. So they point, as I said, this is all magnetic. The question, of course, is what the origin of magnetic fields. That's another talk. Maybe Yanis has already given that, and I'll stop here. And I'll thank you. Thank you very much.
Thank you, Demo, for your nice talk. Maria, will you take questions or?
I think that you can take questions.
Okay. So is there, please, any questions from the audience?
Can I make a comment?
Of course.
Apostole?
Sure, sure.
Okay. Dimo, very nice presentation. Thank you. I've been thinking only on black hole X-ray binaries.
Yes.
And I don't know. I'm always scared of AGN. So many people work.
Yes, that's true. There's more phenomenology there. There's no question about it.
Yes, yes. No, so I want to make then a comment. AGN are lazy. They do things in millions of years.
Yes.
Black hole X-ray binaries do it in a year. So if you miss this outburst, you'll catch the next one. And so we have a lot more data and correlations. In black hole X-ray binaries, Pablo Reg, to the surprise of all of us and the entire community, showed that the delay of the hard X-rays with respect to the soft ones are correlated with the spectrum.
Okay.
So it's not okay, because if the time lags are coming from propagating fluctuations, then they don't talk to the spectrum. The spectrum is produced.
People claim they talk, but anyway.
They don't, but they don't. You have to give. One has to give a one has to give a physical picture for this.
Yes, of course.
But if the if Comptonization does both produces both the hard X-rays and the time lags,
yes,
which are naturally, then it is natural to be correlated.
Of course.
So
that's something we've been agreeing for many decades now.
Yes. Okay. The only advance since the time that you published the paper with Hua and Titarchuk, with the corona where the density goes as 1 over r, Pablo and I have been trying to say that this can happen in the jet.
Of course.
But
of course.
Nobody pays attention.
Yeah, well, Nico, that's a story of our lives. Huh?
That's okay.
I agree with you. I mean, I don't certainly want to stick to the corona only. It could be Comptonization. There's outflows, and the outflows could be basically even across the disk. But of course, as you go farther out, the temperature is probably low, but there'll be some outflow from nearby, which they can do exactly what you and Pablo discussed. And the important thing is that the density profile cannot be too steep, otherwise you don't get enough scattering. So the relatively shallow density profile, whether it's a jet or whatever we call it, or the corona, it's in some sense necessary. And I'm sure you agree with that.
Yeah, the observations tell us whenever we can resolve a jet near its base, we see it is parabolic. And in a parabolic jet, the density goes as 1/r.
Yeah, I see. Okay.
So we have observational evidence that the base of the jet, in the base of the jet, the density goes as 1/r.
I would not disagree.
Okay. No, it was just a comment.
Yes, fine, sure.
Yeah, and yes, I like very much that you gave a physical picture for what the people draw in cartoons.
Well, the issue is exactly the thermal and non-thermal, what's called non-thermal, which is probably quantization. That's the point. This is something for the galactic sources has to be understood also. Not everything scales, of course, accurately, but well, it's up to observations now. We have, at least I provide some kind of a framework with this, which you can understand basically absorbers and X-ray emission. This issue about the accretion in black hole being more, the accretion rate in the black hole being much smaller than what you observe from X-ray spectroscopy. It was done for GRS 1915 minus 104, whatever that is. It was Julia Lee with Joy Nielsen. Just from one line, they had one line, low ionization line, and they have the velocity. It was so from the ionization state, they could calculate the distance, and therefore they can, and then from the line, they could calculate the velocity, and therefore they had basically, they can calculate the mass flux far away, and they found out it was much higher than there was by at least an order of magnitude, but you need to power the black hole even with low efficiency. So these are issues that presumably the new satellites will help resolve. Now, the question is, anybody will pay attention to that, or just gonna go back to the, how they call it, the lamppost? Well, the lamppost is useful, but is that really the lamppost above exactly above the black hole, or it is a lamppost that, well, some kind of thick disk that extends all the way to tenths of Rg or 100th of Rg for a low luminosity AGN, or even for the galactic black hole at low accretion rates. There is a more recent calculation from Kara et al. With Neisser, and they did exactly the lags of the hard with the soft, and they came up to the answer. They assumed that the accretion disk goes all the way to ISCO, and they found that when the luminosity went high, the lags decreased, and therefore she said, well, the disk goes all the way to ISCO, and the corona is, I don't know, 30, 40, 50 Schwarzschild radii, but then the corona collapses. Well, I don't know. I mean, my guess is that not only the corona collapses, but also the disk, the truncation will also move inwards when you increase the m dot. There's no answer to those issues unless you are able to image these objects. And since there's no chance of imaging, we have to work with these models. If we accumulate enough data, then hopefully there is some models will be preferred because they can explain a large body of data with smaller parameters. That's all I can say about what the future of this kind of enterprise.
Okay, I will not monopolize. I will stop. Other people can ask questions.
Any other question?
I have a question.
Go ahead, yes.
Or two. Yes. So it was a very nice overview, and maybe you said it, but I missed it. So I was wondering how some observations about the time lags between the different UV filters and the X-rays that are measured in some AGN
Yes.
fit into
I mean,
the
the
spectrum
reverberation
because-
mapping that were people talking about, the X-rays, and then they try to follow them with the UV and
Yes,
yes.
and there are some ideas that even the simple, the standard Sakura-Sunayev model in certain cases can predict very nicely, or it is in agreement with the lags measured in the UV filters, but there is a disagreement with the measured lag between UV and X-rays. And I was wondering how this, the model that you described with the transition between the puffed up disk and the thin disk.
I will have Sifi ask the question. Sifi, you're the expert on the correlation between X-rays and optical UV. Maybe you'll answer Maria's question. Is Sifi there?
I don't see. Maybe
he's gone home.
Left.
We are getting late, maybe.
Okay.
Well, all right.
And another one.
Yes, go ahead.
Which is a short one again. It is related to the FK alpha line and the measurements of and the use of that in order to measure the spin of the black hole.
Okay.
So in your framework, where exactly does the FK line come from, and is it totally unrelated with the spin of the black hole?
Wow. Well, now I'm going to become totally politically incorrect. They're going to disbar me. I don't. The answer is I do not know. The standard answer is that we have an accretion disk that goes all the way to the ISCO, and but I showed you spectra that they have absorption features and there's no emission. What is the emission there? I don't think well, of course, the talk is about absorption. Sometimes we have emission, but sometimes we don't have emission. The question is, if the disk is there all the time, where is the emission? And that's part of the line part, which I didn't want to get involved. Maybe it'll be another talk in that respect. So that's something that whenever you absorb something, it doesn't say absorbed. These photons don't disappear; they get emitted. So we had some discussion with Bihar on that issue, and you see the emission usually appears, at least for this object I show you, there is emission at the very low ionization lines, which means that the emission comes from far away. The iron line, of course, I assume that's ADAF, but it cannot be an ADAF. Maybe it has an additional component in there. I don't want to add components without really being necessary. Before I add components, I like to see the correlations of when the line appears and how strong it appears with other aspects of the spectra, AGN or galactic sources. If you ask me off the top of my head, I have my name and a paper with that we claim that if you have scattering in the wind, you can broaden the line in one scattering. So that's in some sense, if you would like to have an answer, then if the wind is sufficiently dense, high M dot, then you're close to Eddington, then the wind is relatively thick. So if you produce the line, then you can produce it with recombination. It doesn't have to be really fluorescence. And then we have winds everywhere. So the line has to scatter to come into your line of sight. And if it scatters in the wind, and as I said, the column densities are not necessarily very small. If it scatters in the wind, then you can get a redshifted line. And well, the observers can correct me here, but every time I see anybody discussing about this issue, they talk about the redshifted piece of the line. Usually you observe more prominently the blue shift of that line. And I don't know, somebody in the audience maybe knows the answer to that. Maybe Yorgos knows it. he smiles, but he's not going to say anything. So, so no more questions. Okay. Well,
And let me make sure. Any other question?
how many people are there anyway?
30 right now.
How many?
30.
30. Okay. Well,
During your talk, they were 44 or 45.
okay. Well, what can I say?
This is a good number.
I hope no, but I hope that somebody will have some questions.
Yeah.
But as I said to I usually ask questions, and they say, "Well, you ask so many questions." I said, "Well, I don't want to have a speaker come up with no questions. It's like nobody asked you to go with him to the prom, you know." So, you have to ask questions so I can show the speaker somebody understood something. Maybe maybe it was too confusing. I don't know. Yeah, you tell.
What are you doing with abundance? As you said, you didn't pay it too much attention.
Which one?
Abundance of the.
The abundance is no. Well, we usually assume solar. However, we have a paper with this. It will come out. Just got accepted in UpJ, where we show 3 different observations in the hard and the soft state of 3 galactic binaries, and we also show some of the simulations with the for Prism and Athena, and in there we also play around with abundances. I don't like to play with abundance. If it doesn't agree, doesn't agree. I don't think it buys you anything. If you have some, they may force you to have some abundances which are a little higher, but you have to have lots of data that really cry out for higher abundances. But you don't have to really. If you change the normalization, if the disk is not, if the wind is not a single power law, and you find that solar abundances can fit the large part, that don't fit the faraway part, the low ionization, that don't fit the low ionization, and you can fix that with higher solar abundances, you could change also the normalization there. And maybe the wind, that is not a single power law, it's a broken power law. How do you know that? You don't know that. So I would be, personally, I would be not willing to mess around with abundances, but
You have not tried something like a broken power law, you said.
No, just
simply a single
power law. Yes, the models assume a single power law, and maybe it could be very wrong, because the power law, actually, the power law may change from one state to the other, because we've seen in some states we have very little line absorption. So a steep power law will give you that, because the inner part of the wind is fully ionized, and by the time you go farther out, if the power law is steep, then there's not enough column. So if you don't have enough column because the power law of the wind is steep, then you don't have any absorption. On the other hand, now if we, with Athena, where there is some indication for absorbers there, but very weak. That's because your noise level is high. But if you beat down your noise level by a lot, then all of a sudden you find that there are absorption features, and you have to deal with those. In general, yeah, go ahead.
Yeah, okay.
Okay. Well, I think that that pretty much does it, right?
Mm-hmm.
Okay, guys. Thank you very much. I really appreciate seeing you.
We thank you very much for coming.
Thank you.
And if you have any more questions, you can write to me. That's I'll be more than happy to answer your questions.
Okay,
Sure.
thank you.
Okay.
Okay.
Thank you.
All right. Thank you. All right.
Καλή σας μέρα.
Γεια σας.
Έχουμε και μια διαφορά.